Hi, and welcome to my presentation on diabetes risk prediction using ML on BRFSS data. As you may be aware, diabetes is a significant health issue, especially in the US, where it has affected 38 million people, which is about 12% of the US population in 2021. This only continues to grow as people are forced towards cheaper and oftentimes unhealthy dietary options. However, within these numbers also hold significant statistical power that can be leveraged with the help of machine learning to potentially detect diabetes in undiagnosed patients, thus leading to early and proper diagnosis and preventive treatments. Here I apply machine learning techniques on a telephone survey dataset collected in 2015 by the Behavioral Risk Factor Surveillance System, or BRFSS, which is managed by CAC. There were 22 questions, including if they had been diagnosed with diabetes, which is my target predictor. The questions asked range from medical, like if they have high blood pressure, to dietary, like if they eat their fruits and vegetables. You can see the distribution of my features in Figure 1, where it has been split on the diabetes outcome. I took this dataset, cleaned up a bit, as well as balanced the data to ensure equal numbers of yes and no labeled diabetes, and then split the data into a train set for training and a test set for final model validation. I started with an initial broad approach to see which machine learning methods would stick and perform the best on this dataset based on the accuracy metrics. As you can see in Figure 2, I was able to narrow down to 3 models: Boosting Tree, ElasticNet, and Support Vector Machine. SVM was picked even though it was 5th in the list because Lasso is technically part of ElasticNet if its alpha parameter is set to 1, and linear discriminant analysis has very limited tuning power, thus limited capacity to be improved upon. For each model, I used a rough and fine-tune approach, along with 10-fold cross-validation to search for optimal parameters and model consistency. This rough and fine-tuning approach is a two-tiered in the sense that I initially explored a large range of values for each respective hyperparameter. Once I was able to identify values that roughly performed well, I fine-tuned my search to values closely around these found values to identify the real optimal parameter that was not allowed to be considered the first pass. As you can see in Table 2, the Boosting Tree barely came out on top in the train and test set datasets, with only a 0.4 and a 0.3% advantage respectively. But when we scale this model prediction to a large population, a small percentage difference could still mean hundreds to thousands of patients more that would be accurately classified. But unfortunately, with a top accuracy of about 7%, I still would not deploy my current models in real-world settings, because this would mean 1 in 4 patients will potentially be misclassified. But some key takeaways that my models do provide are these feature importance and coefficient graphs shown in Figure 3. You can see here in reality there are only a few of these 21 features in the dataset that had impactful and meaningful contributions for modeling, such as high blood pressure, BMI, and high cholesterol, all of which are medically significant in relation to diabetes. This is also nicely reflected in the data distribution shown earlier in Figure 1, in these respective features as visually higher red bar proportion to blue bars for those labeled with diabetes. For the coefficient graph, this is also reflected in the center area where many of the values are close to 0, thus contribute little to none for classification outcome. But in order for me to deploy my models for diabetes risk prediction, I need to significantly increase my accuracy score. I would like to go back and consider heavy feature selection in my pre-processing steps for my datasets, hoping to remove as much of the noise from the signal as possible prior to my models being trained. But nonetheless, this outcome still provides significant insight towards the path in predicting diabetes from telephone collected survey data. Thank you for listening to my presentation, and thank you, Adam, for a wonderful course in machine learning. Happy holidays.